Welcome to this Altera online training entitled How to Begin a Simple FPGA Design. My name is Steve. This training module is in the form of a flash movie that consists of a short presentation followed by a demonstration that will show you how to create a simple, fully functional, programmable logic design in under an hour using the Quartus II software. While watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training or the demonstration at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. You've probably been hearing a lot of great things about FPGA devices and their use in digital logic designs. You may have even heard FPGA design success stories from your coworkers or business partners. However, you personally haven't created an FPGA design yet. You may be thinking that creating an FPGA design is hard to do, or that the benefits of including programmable logic in your system design would be minimal. These perceptions are untrue. Even if you've investigated the use of programmable logic for your designs in the past, today's FPGAs are very different and have far greater capabilities than even a few years ago. And creating such a design is actually very easy using freely available software tools such as the Altera Quartus II software. This training module will provide you with some basic information about FPGA devices, the benefits of using them, and how to create designs for them. A demonstration will then show you how easy it is to create a simple FPGA design. With this training, along with other Altera training modules and tools, you'll see firsthand what you've been missing and how you can jump headfirst into the exciting world of programmable logic. Here is the agenda for this training. First, we'll take a short look at exactly what is an FPGA and some of the benefits of using these devices. Then, a self-playing demonstration will show you all the steps required to create your first FPGA design using the Altera Quartus II software. The design shown in the demonstration is targeted to an Altera Cyclone 3 device found on Altera's Cyclone 3 FPGA Starter Kit development board. Cyclone devices are Altera's high logic capacity, low-cost family of FPGAs. If you have the Cyclone 3 FPGA Starter Kit, you can immediately program the completed design onto the Cyclone 3 device to help you understand the entire programmable logic design flow from start to finish. If you'd like more information about this kit or how to purchase it, click the link highlighted here. After the demonstration, we'll look at what else you can do now that you understand the very basics of the FPGA design process. You'll also be directed to resources where you can go for more training or get further information about Altera's products and services. Let's get started. Engineers today are faced with more challenges than ever before. Electronic OEM companies are pushing their engineers to design new products in less time and with fewer resources, while still demanding higher performance and better differentiation from competitive products. Engineers are also faced with technologies that are rapidly changing and customer requirements that seem to differ from one customer to the next. Engineers have to ask themselves, when considering the use of new technologies in their designs, whether they will get a good return on investment to make sure that using the latest and greatest technology is even worth it. These issues are causing a lot of stress for today's design engineers. Programmable logic devices, such as FPGAs, have been around for over 20 years. They provide many benefits to help solve these issues. FPGA devices provide a flexible, customizable, low-cost solution that can substantially shorten a design's time to market. They're made with leading-edge technology. Some of the newest Altera FPGA devices are the first 28 nanometer technology devices in the industry. FPGAs provide quick programmability and reprogrammability that make the ability to update a product once it is out in the field a reality. Creating and implementing an FPGA design is also very easy. Designs created using the Quartus II software can support a group-based design methodology, so different members of a design team can work on different parts of the design with the knowledge that everything will work when the pieces are put together. While the use of an FPGA device might help solve only one or only a few of the specific engineering issues discussed here, programmable logic in the form of FPGAs has emerged as the technology of choice to best handle the entire group of issues overall. With each new generation of FPGA, more and more features and functions are built in. How does this affect things at the system level? It means that functions on a board done with dedicated external devices such as the CPU, I/O cells, and the DSP shown here can now be incorporated into a single FPGA device. This reduces the overall device count, which in turn reduces the size of the board. Both of these factors affect board cost and power usage. One of the main reasons that engineers love FPGA devices is that you can't make any mistakes. If you do make a mistake with a design, you can simply erase the device, debug the problem, and start over. At most, this will cost you some time, maybe a few hours or a day, depending on how complicated the design is and how long it takes for the FPGA design software to recompile the design. The same can't be said for ASIC devices. If a problem is found with an ASIC after it has been fabricated, a completely new revision of the die must be fabricated, costing not only time on the order of weeks, but also a lot of money. FPGAs are very easy to get into for anybody with any level of design experience. From students creating simple designs while learning the FPGA design process, to experienced ASIC designers, anybody with any amount of digital logic design experience can get started with FPGAs. Finally, Altera offers a complete one-stop shop solution. Altera designs the chips, fabricates the wafers, packages the die, and has devices available on the virtual shelf of the Internet for anybody to purchase and use. Altera also actively develops and updates the Quartus II FPGA design software to fully support all the features of available devices, as well as prepare users for the exciting new features available in upcoming devices. There is a lot to love about FPGAs. Here are some of the key features of a modern-day FPGA architecture. Different FPGA families and devices within those families will have a different mixture of these basic FPGA building blocks. The hardware structures highlighted here are selected by the FPGA design software based on the user's design and other design settings. The design software selects the appropriate structures to meet the user's design goals, whether it's to get the best possible performance or to use the least amount of power. The FPGA architecture is dominated by logic in the form of logic elements, or LEs, arranged in a grid throughout the device. LEs consist of two parts: lookup tables that implement combinatorial logic functions such as AND and OR gates, and registers which implement synchronous logic such as D flip-flops. Besides LEs, other dedicated hardware structures are available for implementing functions and improving performance. These special device resources are usually arranged in columns throughout the device. One type of dedicated resource is embedded memory. Embedded memory blocks may come in different sizes and can be cascaded in serial or parallel to implement larger memory structures. Embedded multipliers, also arranged in columns, come in different shapes and sizes and can be cascaded together in a similar fashion to implement more complicated DSP functions. Most devices include multiple high-speed phase lock loops, or PLLs, to implement complicated clocking structures. All devices consist of a large number of user-selectable I/O elements that can be placed and configured to connect the FPGA design to other external devices on the printed circuit board. All of these device resources are connected together through a routing fabric that is set up and controlled through configurable registers. The routing is extremely flexible, ensuring that the hardware required for a particular design will get connected correctly and in such a way as to meet all design goals. Now that you know what FPGAs can do, and a little bit about what's inside an FPGA device, how do engineers design with them? First, you need to come up with an idea, either at the system level or a design specific to the FPGA. The design idea is usually documented in one form or another as a specification for what the FPGA design should do and how it should work. Second, you need to describe this idea in a form that is understood by the FPGA design software and can be translated into the hardware structures found in the device. This is usually done in the form of a high-level hardware description language, or HDL. Verilog HDL and VHDL are the most popular languages used for creating FPGA designs. Next, FPGA design software, such as the Altera Quartus II software, takes your code and performs a process called compilation. Compilation is made up of two main steps: synthesis and place and route. Synthesis translates the design code into available hardware structures on the device. Place and route chooses the actual hardware structure locations and then connects them together using the configurable routing fabric. Compilation also checks to make sure there are no errors in the design, ensures that the design will fit into the target FPGA, and guarantees that the design is operating at the performance specified. The software outputs a binary programming file that contains all the information required to program the target FPGA device with the design. Finally, you download the design into the target device using the programming file and debug your design's functionality directly in hardware. The programming can be done through a flash ROM or through a direct connection from a computer to the FPGA device. If you find an issue with the design, you can simply go back to the design code or software settings, make changes, recompile, and reprogram the new programming file into the FPGA. As you can see, this process makes it very easy to fix problems and make changes to a design in a minimal amount of time. Now that you've seen a brief overview of what an FPGA is and some of its benefits, let's look at how to create a simple FPGA design using the Altera Quartus II software. This demonstration will walk you through the My First FPGA tutorial PDF available from the Altera website and linked here. Before watching this demonstration, you may want to download and install Altera's free version of the Quartus II software. With the Quartus II software installed, you'll be able to follow right along with the demonstration and PDF tutorial tutorial document linked from the main training window. You can download the free web edition directly from the Download Center at the Altera website. Select the web edition. If listed, select a specific product. Select a specific product. In this case, select to download the web edition that includes Service Pack 1. If you're interested in finding out more about the Cyclone 3 FPGA Starter Kit, or you have already purchased the kit and want to download software or documentation, go to the Development Kits and Cables selection from the Design Tools and Services list. If you already have the Cyclone 3 FPGA Starter Kit and you want to program the Cyclone 3 device with the design you'll have at the end of this tutorial, it is recommended that you go through the Starter Kit's Quick Start Guide included with the full kit installation download and set up and connect the board to your computer. Plug in power for the board and connect the USB cable. You'll need to install the USB blaster drivers included with the board to establish a JTAG connection for programming the Cyclone 3 device. See the website and the Quick Start Guide for more details. Once the Quartus II software is installed, you can start the program from the Start menu or the shortcut created on the desktop. To start creating an FPGA design, you must first create a project. A Quartus II project is required to contain and manage all the files that make up the design. The easiest and quickest way to create a project is with the New Project Wizard. You can start the New Project Wizard in a number of ways. In the Start Project folder in the Tasks window, you can double-click Open New Project Wizard. Or you can access the wizard from the File menu. The New Project Wizard is just like any other software wizard you may be familiar with, asking for the minimal amount of information to quickly set up the project. First, specify the directory where all the project files should be stored. Next, give a name to the project. Any name will do. Finally, specify the name of the top-level design entity. All projects must have a top-level design file that connects all the pieces of the design together. The wizard has other pages for entering information, but they're not needed for this demonstration. The new project has been created. Now, the target FPGA device will be selected. All projects must target a single FPGA device. In the device settings, accessed from the Assignments menu, the target FPGA device is selected by device family and by specific device properties. This project will be used with the 324-pin Cyclone 3 device found on the Cyclone 3 FPGA starter kit, so this device will be selected. If you are going through this tutorial with another Altera development kit, select the appropriate device for your kit. There are many similarly named devices within each device family. Make sure you select the correct device. Using the filters, as shown, makes it much easier to do this. You can verify the selected device and the name of the top-level design entity in the Project Navigator. Now we'll start creating the design. As discussed earlier, most designs are created in an HDL, such as Verilog or VHDL. In the Quartus II software, you can create designs using these HDLs, or you can create a schematic design. In this tutorial, a combination of these design techniques will be used to create the full design. To start, the top-level design file will be created as a schematic design. This is a good method for creating a top-level design because the visual nature of a block schematic design makes it easy to see how all the pieces of the design are connected together. You can create new design files from the Create Design task, from the File menu, or from the New File button in the toolbar. To make sure the new schematic file is used as the top-level design file, it must be saved with the same name entered earlier in the new project wizard. The tutorial design is a binary counter intended to light LEDs on the Cyclone 3 FPGA starter kit board. To start creating the design, a simple counter will be created using Verilog and added as a schematic symbol to the top-level design file. A new Verilog design file is created in the same way as the schematic file. The file will be saved as simplecounter.v. With the Verilog file saved, a schematic symbol can be created for this counter design from the File menu. Creating a symbol like this creates a black box for the design. This is essentially a box with inputs and outputs that contains internal logic, but it is not necessary to know how the internals of the box work for it to work correctly with the rest of the design. You can switch between files by clicking on the tabs near the top of the window. The counter symbol must now be added to the schematic design. This can be done by selecting the Symbol button in the toolbar, or by right-clicking or double-clicking in the schematic. The Symbol dialog box lets you select existing symbols and create new ones. The new counter symbol is located in the project library. You can see that the simple counter black box symbol only displays the clock input and the counter out outputs. The symbol is attached to the cursor and may be placed anywhere in the schematic by simply clicking. To add more to the schematic, the Symbol dialog box must be reopened. Next, a clock source must be created for the counter. The clock will be created using a phased lock loop, or PLL. A PLL is a specialized circuit found in FPGA devices that is used to generate output clocks of user-defined frequencies, phases, and duty cycles based on an input clock, usually a clock coming into the device from the board on an input clock pin. To quickly create the PLL for this design, a tool called the MegaWizard Plugin Manager is used. The MegaWizard Plugin Manager is another software wizard in the Quartus II software. This wizard lets you create customized, parameterized blocks of commonly used logic using a simple graphical interface. The PLL is found in the I/O group of installed MegaWizard plugins. The PLL will be created in Verilog code and optimized for the Cyclone 3 device family. The name given to this created instance of the PLL will appear on the symbol that will get added to the schematic. The MegaWizard lets you parameterize the PLL and immediately see the results of changes you make in the graphical symbol on the left. First, we'll specify the speed grade of the Cyclone 3 device and the input clock frequency provided by the Cyclone 3 FPGA starter kit board. The input frequency is 50 MHz. Next, options that are not needed for this design will be turned off. Again, notice how the graphic on the left updates as changes are made. We'll now skip ahead in the MegaWizard and configure the PLL output clock. The output clock should be only 5 MHz, so a division factor of 10 will be used. Clicking Finish displays a summary of the files that will be created by the MegaWizard, including a .bsf file, which is the symbol file format used by the schematic editor. Clicking Finish again closes the MegaWizard. With the PLL in place, a connection between its output clock pin and the simple counter's clock input pin can be made using the orthogonal node connection tool found in the toolbar. It won't be necessary to manually switch to this tool in this example, since hovering over a symbol's input or output pins automatically switches to the tool. Now, an input pin and an output bus will be added to the design. The input pin is needed so that the input of the PLL can be connected to a device input clock pin. Pins can be added through the symbol dialog box or from the pin tool in the toolbar. You can place symbols touching each other's pins and then drag the symbols apart from each other to automatically create connections. Double-click a pin's name to change it. In this case, we'll change it to OSC clock, since the input clock is coming from a clock oscillator on the board. Now, an output bus from the counter will be created using the orthogonal bus creation tool. To set a name for an object, such as this bus, right-click the bus, right-click the object and select Properties. The bus is simply named counter 31 to 0. The most significant bit is always listed first. The final design component will be a multiplexer. The mux will route certain output bits of the counter to the external LEDs on the board. Selecting more or less significant bits using the mux will create a slower or faster count on the LEDs. The mux is also created using the MegaWizard plugin manager. The mux is found in the Gates folder. As with the PLL, the mux is configured using the options available. This mux will have two 4-bit inputs and a 4-bit output. Again, a symbol file is created for the generated component. To connect the mux inputs to the outputs of the counter, the orthogonal bus creation tool will be used again. A bus is required on the output of the mux to connect to output pins. To give you more space when drawing a schematic, you can detach the schematic editor from the main Quartus II interface. The first, slower counting input to the mux will use counter output bits 26 through 23. Naming the bus appropriately automatically creates the required bit slicing for the mux input. Bits 24 through 21 on the second mux input will produce a faster count on the LEDs. As always, it's good practice to save your work. Save early, save often. Next, we'll add output pins to the output bus of the mux. The output pins are named LED 3 to 0. Finally, we'll add one more input pin to control the select line of the mux. This input will get connected to a button on the board to control the speed of the displayed count. The design is now complete. If you want, you can add notes using the text tool to provide information about the design, such as the function of the button input. With the design complete, the schematic editor can be reattached to the main interface. Next, I/O pins must be selected for the inputs and outputs. Before we can start creating I/O assignments, a process called analysis and elaboration will be performed. Analysis and elaboration is the very first step of the synthesis process. It will check to make sure that there are no errors in the design, and it will establish the project's design hierarchy. Whenever you perform a compilation process, the compilation report will open automatically and update as the compilation proceeds. You can find lots of valuable information about how the compiler interpreted your design using the compilation report. This information is invaluable for debugging. There were no errors found, and the design hierarchy has been established. To create pin assignments, we'll use a tool called the Pin Planner from the Assignments menu. The Pin Planner makes it very easy to create I/O assignments for all the I/O in the design. There are a number of ways to make these assignments. You can drag and drop a signal from the All Pins list here onto a pin in the main package view. You can also double-click a location cell and select a pin from a list. You can also simply type in the name of a pin. Fill in the rest of the pin locations based on the development kit you are using. The correct pins must be selected to make sure that the clock, button, and LEDs on the board are connected to the design correctly. Before the design can be fully compiled, timing constraints must be created. Timing constraints tell the software how to place and route the design in order to meet timing requirements. You create timing constraints in a new text file with a .sdc extension. One way to do this is to start the TimeQuest Timing Analyzer, a tool that lets you create constraints and generate timing reports to analyze whether a design will meet timing. The Timing Analyzer can be accessed from the Tools menu or from the Quartus II toolbar. Create an SDC file from the TimeQuest File menu. A new text editor file appears. As before with the Verilog design, we'll copy and paste the timing constraints into the SDC file to save time. These constraints tell the software that the input clock to the design is 50 MHz and that the timing analyzer should automatically derive other timing constraints for the design from this information. Saving the SDC file with the same name as the top-level design file automatically adds it to the project and applies the constraints to the schematic design. The design and all the assignments and constraints are now complete. To fully compile the design, you can select Start Compilation from the Processing menu or click the Play button in the toolbar. The design has successfully compiled. An SRAM object file, or .sof, was created in the project directory by the compilation. This is the file used to program the target device. If you have the Cyclone 3 FPGA starter kit, you can now program the Cyclone 3 device with the design using the .sof file. Before programming, make sure the board is powered on and connected to your computer with a USB cable. To program the device, open the Programmer from the Tools menu. Before the programmer can be used, the programming hardware must be set up correctly. Click the Hardware Setup button to select the programming hardware. The Cyclone 3 FPGA starter kit includes built-in programming hardware referred to as a USB blaster. Some boards require a separate USB blaster cable to program the target device via a JTAG connection. In either case, the USB blaster should be listed under available hardware. If it is not, you'll need to make sure you've properly installed the USB blaster drivers. Check the development kit or USB blaster documentation for details. If the USB blaster is listed, select it from the pop-up list and close the dialog box. The Cyclone 3 device and the .sof file should already be listed in the programmer. If they aren't, click Add File to add the .sof file found in the project directory to the list. Make sure the Program Configure option is enabled in the checkboxes on the right. When you're ready, click Start to program the device. The programming is complete when the progress bar reaches 100%. When it's done, you should see the 4 LEDs on the starter kit board counting as seen here. LEDs are active low, so the count will begin with all LEDs turned on. To speed up the count by viewing less significant bits of the counter, push and hold button 1 on the board, as seen here. Congratulations! You've created an FPGA project from scratch and went through design entry, assignment creation, compilation, device programming, and verification in hardware. Continue the training to find out how you can learn more about getting into the exciting world of programmable logic. If you want to learn more about FPGAs and designing with FPGA devices, here are 3 recommendations. First, if you have not already done so, download the web edition of the Quartus II software from the link shown here. It's free and fully supports all Cyclone series devices. Second, as mentioned earlier, you can purchase your own Cyclone 3 FPGA starter kit. The kit includes everything you need to start creating FPGA designs. Don't forget to ask your local Altera sales team if there are any promotions or discounts in your area. Finally, contact your FAE Altera sales representative or check the Altera website to learn more about Altera training, Altera documentation and support, and Altera's complete device product portfolio. Altera provides a number of options for further training. You can enroll in other online trainings or attend one of our many instructor-led training courses. Visit the training section of the Altera website for more details about the courses available and how to register. For further information about using the Quartus II software, be sure to check out the online help as well as the Quartus II handbook. There, you'll find detailed information and multiple examples to help you use all of the features of the Quartus II software effectively. You can always visit my support to get help from Altera applications engineers, or call the hotline to get live assistance. For local assistance, contact your local Altera sales office to speak with a field applications engineer. Check out the Altera wiki for up-to-date articles written by Altera engineers. The online Altera forums are a great place to connect with other Altera users, to share experiences, and find solutions to common issues. You can order official Altera literature by mail or download it from our FTP site. Finally, be sure to check out the Altera website to find solutions to the most common technical questions and problems and view design examples. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us to create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this online training on how to begin a simple FPGA design.